In the previous lecture, we have studied about round-robin scheduling and we have seen how it works. So in this lecture, we will be seeing how we can calculate the turnaround time and waiting time for round-robin scheduling. So we will be taking an example of a CPU that follows round-robin scheduling, and we will see how we can calculate the turnaround time and waiting times for the set of processes in that. So here, consider the following set of processes that arrive at time 0 with the length of the CPU burst given in milliseconds and time quantum taken as 4 milliseconds for round-robin scheduling. So here we are given a set of 3 processes with process IDs P1 to P3, and their burst times are given in milliseconds. So P1 has a burst time of 24 milliseconds, P2 of 3 milliseconds, and P3 also of 3 milliseconds. And we assume that all these processes arrive at time 0. So the arrival times for processes P1 to P3 is time 0, and the time quantum is taken as 4 milliseconds, and it follows a round-robin scheduling. So if you remember what I taught in the previous lecture about round-robin scheduling, we have seen how it works. So there we saw that in round-robin scheduling, we have a particular time quantum, which is a particular amount of time that will be assigned to each processes for their execution. So a particular process will be allowed to use a CPU for a particular quantum of time that we define, and once that time period expires, the process will be preempted and the next process in queue will be given the CPU for its execution, which will also be allowed to use the CPU for a particular time quantum, and then it will be preempted and the next process will be given the CPU, and so on. So that is how a round-robin scheduling works, which we have explained in detail in the previous lecture. So here in this example that we are taking, the time quantum is 4 milliseconds. That means each of the processes will be allowed to execute for 4 milliseconds, and after that the CPU will be given to the next process in the queue, which will also be allowed to use a CPU for 4 milliseconds, and then that will be preempted, and so on. So here the time quantum is 4 milliseconds. So here we will be seeing how we can calculate the turnaround time and waiting time for this set of processes. So the first step in calculating this turnaround time and waiting time for any scheduling algorithm that we have is to first form the Gantt chart. So we have to form the Gantt chart for this set of processes, and after that we will be proceeding to calculate the turnaround time and waiting time. So let us see how we can form the Gantt chart for this. So here I have shown how the Gantt chart will be formed, and I will be explaining this, but before that keep in mind that here we are following round-robin scheduling and we are to consider the time quantum which we have, and the time quantum is 4 milliseconds. So 4 milliseconds is our time quantum, keep this in mind. So we know that all these processes P1 to P3, they arrive at time 0. So they are waiting in this order, P1, P2, P3 in the ready queue. So P1 is the first one that we have, and P1 will get the CPU at the 0th millisecond. So when P1 gets the CPU, it has to execute for how long? The burst time of P1 is 24 milliseconds. But will it be allowed to execute for 24 milliseconds? No, because this is round-robin scheduling and we have a time quantum, and it will be allowed to execute only for that particular period of time, which is 4 milliseconds in this case. So P1 will be executed for 4 milliseconds. So from 0 to 4 milliseconds, P1 executes. And after that what will happen? P1 will be preempted and the CPU will be given to the next process in the queue. So which is the next process in the queue? It is P2. And what is the burst time of P2? P2's burst time is 3 milliseconds. So at the 4th millisecond, P1 is preempted and P2 now gets the CPU. Now P2 also will be allowed to execute for 4 milliseconds, which is the time quantum. But we see that the burst time of P2 is only 3 milliseconds. It is less than the time quantum. So it will execute only for 3 milliseconds. So P2 executes for 3 milliseconds, which is from 4 to 7. So at 7 milliseconds, P2 will voluntarily release the CPU because its burst time was only 3 milliseconds, which is less than the time quantum. So we don't have to preempt P2, but it will voluntarily by itself release the CPU. Now at 7 milliseconds, the CPU will have to be assigned to the next process in the queue. So which is the next process? It is P3. So P3 gets the CPU at 7 milliseconds. And how long it has to execute? It has to execute for 3 milliseconds. So again we see that the burst time of P3 also is less than the time quantum of 4 milliseconds. So P3 executes from 7 to 10, that is for 3 milliseconds, and it will also voluntarily release the CPU by itself. So at the 10th millisecond, P3 finishes its execution, and if we look here, there are no more processes here. But what actually happened was that P1, it only executed for 4 milliseconds, that is for the time quantum, but it still has to execute for 20 more milliseconds, because only 4 milliseconds was executed. So if we subtract 4 from this 24, which is the burst time of P1, we see that it has a remaining burst time of 20 milliseconds. So it has to execute for 20 milliseconds more. So what happened was that when P1 was allowed to execute for 4 milliseconds here, and at the time it was preempted, P1 was taken and put at the end of the queue. So the queue looked something like P2, P3 and P1, because P1 is again coming at the end of the queue. So when P3 completes its execution, there is P1 still waiting at the end of the queue. So P1 will have to be given the CPU. So P1 will get the CPU when P3 releases it, and it will be executed for how long? We see that it will be executed only for the time quantum of 4 milliseconds. So P1 executes from 10 to 14 milliseconds. Now, did P1 complete its execution now? No, P1 has not completed its execution. Let's see how much did P1 execute. P1 executed for 4 milliseconds here. Then here P1 executed for another 4 milliseconds, which is 4 plus 4, 8 milliseconds. So P1 still has a remaining of 16 milliseconds to execute. So P1 is still there in the queue. So at the 14 millisecond, P1 will again be preempted, because that is the way round robin scheduling works. After the time quantum of 4 milliseconds, the currently executing process has to be preempted. But we see that there are no other process other than P1 in the queue. So it will be P1 being preempted and P1 itself being given the CPU in this case. So at the 14 millisecond, P1 gets preempted, and again P1 will be given the CPU because there are no other processes waiting in queue other than P1. So P1 will again execute for 4 milliseconds, which is 14 plus 4 up to 18 milliseconds. Now, did it complete? No, it did not complete. Now P1, how much did it execute? Here we see 4, here another 4, here another 4. So a total of 12 milliseconds were executed, and there is a remaining of 12 milliseconds that P1 has to execute, because the total burst time is 24 milliseconds. So again P1 gets preempted here, and again P1 itself gets the CPU here. So from 18 to 22, that is for 4 milliseconds, it executes again, and then here again P1 gets preempted, and again P1 gets the CPU and it executes for 4 milliseconds, and again the same thing happens here. So from 26 to 30 milliseconds, P1 will do its final execution. So if you see, the burst time of P1 is 24 milliseconds, and it executed here for 4 milliseconds, plus 4 here 8, and plus 4 here again, that gives us 12, and if you plus 4 here again, that gives us 16, then if you plus 4 here again, that gives us 20, and if you plus 4 here again, that gives us 24 milliseconds. So that is how P1 completes its execution at the 30th millisecond. So here we see that each process is allowed to execute only for the time quantum of 4 milliseconds. So at the end, even though it was only P1 that was waiting in the queue, P1 will execute only for its 4 milliseconds, then it will be preempted, but since it was the only process in queue, P1 itself will be given the CPU and it was executing again and again. So that is what happens in a round robin scheduling. So if there are more processes, you can do the same thing, and remember that a process that is preempted will be always put at the end of the queue. So all the processes will be executed, and the process that is preempted will always be put at the end of the queue. So keep that in mind, and then you will be able to easily form the Gantt chart for this. Alright, now we have formed the Gantt chart, and now let's see how we can calculate the turnaround time and the waiting time for round robin scheduling. So I've copied down the same table here, which shows our process IDs and the burst time and the Gantt chart that we have formed just now. So now let's see how we can calculate the turnaround times and waiting times. So for this round robin scheduling, there are two methods in which we can calculate the waiting times. So let's see what are those two methods. So the first method is using the formula that we have used for even the other scheduling algorithms. That is, turnaround time is equal to the completion time minus the arrival time. And then the waiting time will be the turnaround time minus the burst time. So from the completion time, that means when the process completely finishes execution, from there if we subtract the arrival time, we'll get the turnaround time. And from the turnaround time that we just calculated now, if we subtract the burst time, then we will get the waiting time. So this method will be useful when you have to calculate both turnaround times and waiting times for a set of processes. So let's see how we can calculate the turnaround and waiting times using this formula for this set of 3 processes. So here I have a table where I have shown the process with process IDs P1 to P3, and here we have the completion times of each of these processes. So to see the completion times, we can just look at the Gantt chart and find it out. If you see for process P1, when did it completely finish its execution? So we see that P1 completely finished its execution over here at the 30th millisecond. So that is the last occurrence of P1 in the Gantt chart. So that will be the completion time, that is 30 milliseconds. Now for P2, when did it last occur? It was here. And what was the time it completed? 7 milliseconds. So 7 is the completion time for P2. And for P3, similarly, it last occurred here, and this is where it completed its execution. So 10 milliseconds is the completion time of P3. Now let's calculate the turnaround time. So the turnaround time for P1 will be the completion time minus the arrival time. So what is the completion time? It is 30 milliseconds. Now what is the arrival time? In the question, it was already given that all these processes arrived at time 0. So they all arrived at 0 milliseconds. So the arrival times are 0 for all the processes that we have here. So the turnaround time of process P1 will be 30, that is the completion time, minus 0, which is 30 milliseconds. Now similarly for P2, what will be the turnaround time? It is the completion time 7 minus 0, which is 7 milliseconds. And similarly for P3 also, the turnaround time will be the completion time 10 minus the arrival time 0, that is 10 milliseconds. Alright, so we can easily calculate the turnaround times like this. So in this question, the arrival times were all 0. So in some other problems, you may have different arrival times. So if you are having different arrival times, then use the arrival times as given in the problem. Alright, now we can calculate the waiting time. So the waiting time is the turnaround time minus the burst time. So turnaround times we just calculated here, and the burst time is what is given in this table. So for process P1, the waiting time will be the turnaround time 30 minus the arrival time 24, which is 30 minus 24, 6 milliseconds. And for P2, the waiting time will be the turnaround time 7 minus the burst time of 3, which gives us 7 minus 3, 4 milliseconds. And finally for P3, the waiting time is turnaround time 10 minus the burst time of 3. So that gives us 10 minus 3, that is 7 milliseconds. So here we have calculated the waiting times as well. So you can use this method when you have to calculate both turnaround times and waiting times. So you can calculate turnaround time like this, and once you have calculated turnaround time, you can easily calculate the waiting time. So now we'll go to the second method, and in this method we will calculate only the waiting times. So this method will be useful if you have to calculate only the waiting time and you don't have to bother about the turnaround time. So here the formula that we have is waiting time equals last start time minus the arrival time minus preemption into time quantum. So this formula may look long, but it is very easy. Let's explain it. So last start time means the last time that the process started its execution. So for example, for P1, we see that P1 started its execution here at 0 milliseconds. But was this the last start time? No, because P1 again started execution here at 10 milliseconds, and here again at 14 milliseconds it started, then again at 18 also it started, then 22, 26 also it started. So we see that the last start time of P1 was 26 milliseconds. This is the last time it started. So when it started at this 26 milliseconds, it completed its execution at 30th millisecond, and after that it did not start again. So 26 is the last start time for P1. And from that we have to subtract the arrival time. So for this example, the arrival times are 0 for all the processes. And then from there we have to subtract the preemption into time quantum. So preemption means the number of times the process got preempted. So how many times did P1 get preempted? Let's see. So P1 got the CPU here and it was preempted and the CPU was given to P2. Then again here we see P1 got the CPU and it was preempted and it was again given to P1. So from here also it was again preempted, and from here also it was preempted, and from here also it was preempted. Now when it got the CPU here for the last time, at this point of time it completed its execution, so there is no preemption happening here. So how many times did P1 get preempted altogether? 1, 2, 3, 4, 5. So P1 got preempted 5 times. So similarly you can check for other processes. So preemption, so here the preemption value is 5. The number of time the process got preempted. So for P1 it is 5 into the time quantum. So with that you have to multiply the time quantum. So our time quantum was 4 milliseconds in this example. So 5 into 4, you have to multiply that. So when you apply this whole formula, you will get the waiting time for a particular process. So let's see how we can do this. So for process P1, what is the last start time? The last start time is 26 milliseconds, as I already explained. This is the last time it started. So look at the Gantt chart and look for the last occurrence of that particular process and see what was the start time. So that is the last start time, 26 minus the arrival time. So we know that the arrival times are all 0 milliseconds for this set of processes. So it is 0. Then from there we have to subtract preemption into time quantum. So how many times did P1 get preempted? I just showed you that it got preempted 5 times. So 5 into the time quantum, which is 4 milliseconds. So into 4. So what is the value that we'll get here? 26 minus 0 minus 5 into 4. So if you multiply 5 into 4, we get 20. 5 fours are 20. So 26 minus 20 is 6 milliseconds. So that is the waiting time for P1. So if you see here also we got the same thing, 6 milliseconds for P1. So similarly, let's calculate for P2. So for P2, what is the last start time? The last start time for P2, where is it? It is here. So if you see in the Gantt chart, P2 occurred only one time. So this is the first and last start time for P2. So 4 is the last start time for P2, and then the arrival time is 0, and then preemption. So how many times did P2 get preempted? We see that P2 was never preempted. P2 got the CPU once and it completed its execution at that time itself. So there is no preemption for P2. So the preemption is 0. So multiplied by the time quantum, which is 4 milliseconds. So that is 0 into 4. So 4 minus 0 minus 0 into 4 gives us 4 milliseconds. So finally for P3, we see that the last start time of P3 is 7 milliseconds. So P3 also got the CPU just once and it completed its execution that time itself. So this is the first and last start time. So 7 is the last start time for P3, and then the arrival time, as we know, is 0, and the preemption. So we see that P3 also was never preempted. So it is 0 into the time quantum, which is 4 milliseconds. So 7 minus 0 minus 0 into 4. So that will give us 7 milliseconds. So if you compare here and here, we see that in both the methods, we are getting the same answer. So this first method can be used when you have to calculate both turnaround time and waiting times. And the second method can be used if you only want to calculate the waiting times. So that is how you calculate the turnaround time and waiting times. Now let's see if we can find out the average turnaround times and waiting times for these two methods for this set of processes. So here we calculate the average turnaround time and waiting times. Average turnaround time for this set of processes were 30 plus 7 plus 10 divided by the number of processes, that is 3. That gives us 47 by 3, that is 15.66 milliseconds. And the average waiting time is 6 plus 4 plus 7 divided by the number of processes 3. That gives us 17 divided by 3, that is 5.66 milliseconds. So similarly for this second method also, it is the same thing. Average waiting time 6 plus 4 plus 7 divided by 3, that gives us 5.66 milliseconds. So in most of the problems, you may be asked to calculate the average turnaround time and the average waiting times. So if you have to calculate both of them, you can use the first method, or if you have to calculate only the waiting time, you can use the second method. So that is how you calculate the turnaround time and waiting time for round robin scheduling. So form the Gantt chart carefully and apply these formulas and you can easily calculate it. And also we see that in this round robin scheduling, the waiting times may be a little longer as compared to other algorithms, because this algorithm is mainly used for time sharing systems. And we have to carefully define the time quantum, because if the time quantum is too long, this round robin scheduling will become like a first come first serve scheduling, and it is not useful. And if the time quantum is too short, then there will be too many context switches happening. So we have to strike a balance between the two in order to maintain the efficiency of this algorithm. So I hope this was clear to you. Thank you for watching and see you in the next one.